The first question we have is about constant pressure and constant density in isentropic flow. I would like to answer first, and then the other two questions which appeared recently. So to start talking about the constant pressure inside isentropic flow, we have to go back a bit and still remember that we had also definition of an adiabatic flow, and there is no heat exchange with the external volume. We have the system which is closed and there is no heat transfer. Since there is no heat transfer, T0 or stagnation temperature is constant. At any point, if we take a look in our space, isentropic flow is also an adiabatic flow. We can select two different points in our volume, point 1 and point 2, and we can write that T0 at point 1 is equal to T0 at point 2. That's simple. So basing on this definition, we're going to extend the flow, the law, going to isentropic flow. What is the difference between adiabatic and isentropic flow? The main difference is that isentropic flow is reversible. So it can go in one direction, the flow, or it can go also to another direction. And from mathematical point of view, we just change the sign of velocities, but the flow can proceed. So this kind of flow can happen. This reversed flow can happen only when we have a constant entropy. So entropy of the reversible or isentropic flow will not change. Since delta S will be equal to 0, we have to remember about the second law of thermodynamics, which can be written in different forms. And it's I wrote it in the left form as a function of pressure here, right? And then in the right part, I wrote as a function of a specific volume. This specific volume, I would like to remember, it's some parameter which is reversed to the density. On this left side, we will answer the question why the pressure keeps constant, the stagnation pressure keeps constant, and on the right side, we will answer why is the density keeping constant. Relation between the density and the specific volume is this. Density is reversed to the specific volume, like this. So it's well known from physics, right? So what we are doing to prove it? We are first rewriting the equation, just simply dividing by t left and right side. Okay, this is step-by-step transformation, which is actually given also in our textbook of Anderson. I just combine it or compile it, the list of equations such a way that they are going one after another, so it becomes clear how transformations are happening. And this is the equation in differential, ds, written in one or the other form in terms of pressure and in terms of the specific volume. After, if we would like to solve this equation, we have to do integral. When we integrate left and right side of this equation, I skipped this part of integration because it's given in the formula in the book. And I would like to show you the final version of the integral. You just integrate left, right side, right? When we are integrating this ratio with denominator of temperature, and we are actually integrating by temperature, this becomes logarithm of temperature. And we also use the equation of state, which is P is equal to density RT. Right? Using this equation of state, we are transforming our temperature to pressure. So we receive just function of pressure. So once we receive this differential equation integrated we can see that in any process, it's not obligatory isentropic process, can be any process, not isentropic process. The change of the entropy between state 2 and 1 will be always positive. We know, right, that entropy cannot decrease. Entropy can be only increase, and so this difference is a positive value. Will be equal to a difference of these two parts. Is the specific heat at constant pressure logarithm of ratio of temperatures at point 2 and point 1 minus gas constant logarithm of ratio of pressures between point 2 and point 1. Same thing we receive on the right side, where the difference of the entropies will be the specific heat at constant volume multiplied by logarithm ratio between state 2 and state 1 plus gas constant multiplied by logarithm of the ratio specific volume 2 minus specific volume 1. Since we are working with isentropic flow, this would be equal to 0. Okay. And using this 0, we can write, just change the order in the right and left part of the equation. We just take the this part, right, put here, and on the right part will be the rest, Cp divided by R logarithm T2 by T1. And here we do the same with the right equation. We take this part, take it to left, and on the right we'll have the rest of the equation. The left part equal to the right part. From the left equation, just solving this logarithm, not natural logarithm, it means that our T ratio of temperature will have power. This power is absolutely same as the power we had in front of logarithm, right? It's the mathematical operation. And here it's absolutely same. We had this coefficient before it becomes a power here. So for us, pressure ratio becomes a function of temperature ratio under some power, and specific volume ratio becomes also temperature ratio under some power. This power is a constant value. Cp divided by R is a constant. It's not a function here, and also here constant. And this constant we actually can rewrite in terms of the adiabatic constant in a such way. I hope you remember how this can be obtained. Just to remember you, I would like to tell you that idea is the following. We write that Cp minus Cv is R, and the second equation is Cp divided by Cv is gamma. So from these two equations, we just find what is Cp divided by R, and it will be a function of gamma at the end. So we are basically solving this equation of two unknown. For the right part of the equation is absolutely same. We just decide what is the Cv divided by R from this equation system. And it becomes just a pure function of the adiabatic constant. And now we can write the final answer to our problem. Is actually the adiabatic law, right? That says that pressure ratio between state 2 and state 1 will be a density ratio powered by gamma, and will be equal to the temperature ratio powered by gamma divided by gamma minus 1, which are also constant values, right? So gamma is constant for air, is equal to 1.4. Gamma is equal to 1.4. So this algebraic expression is also constant. What does it give to us, this final equation? It gives to us that no matter what are 2 points inside isentropic flow, this equation is possible only because the flow is isentropic. We have a relation between pressure and temperature at any 2 points. For example, I have point 1, any arbitrary point, my flow goes by some path to point number 2 here. At this point 1, we had temperature 1, and we had temperature 2, right? And we have also pressure 1 and we have pressure too. So how we go to a stagnation pressure? Very easy. For example, at point 1, flow was completely stopped, so it was stagnation point. And then flow travels very slowly, okay, approximately equal to 0 velocity, but we can consider it's infinitely small velocity. And at point 2, flow also stopped, also have a stagnation point, another stagnation point in the flow. So velocity 1 equal to 0, and velocity 2 is equal to 0. Because the flow is already adiabatic, as we told from the very beginning, we see that temperature 2 is equal to temperature 1, because flow is adiabatic. So, and velocity is equal to 0. So temperature 2 and temperature 1 here are stagnation temperatures. I will put 0 here also. And since the stagnation temperature, we also put stagnation pressure. I will put 0 here. So this is why having constant values of and equal values of T2 and T1, we also have an equal values of P02 and P01. So this is why pressure is constant inside the isentropic flow, because T2 and T1 are equal. So this becomes 1. The right part of the equation is 1. So the left part of the equation is also 1. And it's only possible when pressure values are equal one with another. Okay, so this is a simple explanation why actually the stagnation pressure keeps constant inside the isentropic flow. This is only valid for isentropic flow. Let's make it clear, because this is only possible when we have an entropy difference equal to 0. Okay. If entropy difference is not equal to 0, so we cannot make the further transformation of these equations. So for non-isentropic flow, stagnation pressure is not constant. Ok, I'm looking the question. Professor, pode, por favor, explicar os processos físicos que nos fazem chegar no H0 e no T0? Eu entendi a parte matemática, mas não entendi a aplicação prática. So I'm waiting from Victor to know what is the equation number, and I will answer this question, of course. And meanwhile, I hope my screen is visible very well. Meanwhile, I would like to explain about this question, transformation of integral form of the equation to algebraic equation. So how we go from equation 8.7 to equation 10. Just to remember, because I thought it was perfectly explained in the book, but if you need, I repeat by my words. I hope it helps you to understand about this question. So actually, the energy equation is one of the complex equations we have in a list of the Navier-Stokes equations. In such form, you see it on the screen, equation 8.7. This equation is written in a very simplified form. It does not have viscous energies, viscous works. It does not have chemical sources and other sources of energies we might have in the system. And it also does not contain the transient part. So it's a stationary equation. Flow which happens and does not change with time. So this equation consists of two parts. The left part is about the energy flow around the surface of the control volume. This energy flow consists of two sources. It's internal energy, which is E. I will write somewhere here that E is CV multiplied by T, is so-called internal energy, and V is the sort of kinetic energy, right? It's relative kinetic energy when we have not a mass, but we have a density. We have a density here in front, so it's equivalent of the kinetic energy. So here on the left side we have the energy part, Okay, the energy flows through the edge of the control volume, and on the right side we have work, flow of the work created by pressure and flow, and this work is done on the edge of our control volume. Pressure is always acting on the edge, so we must have an area. In this case, we have a very simple control volume. I will try to make it clear. So we have flow entering in our case. So this is edge 1, right? So we have 1, and this is edge 2. We have just one velocity component, which is a horizontal velocity component for a simplified case. We do not have a second velocity component here. So we have just u component of the velocity, and v component of the velocity is equal to 0. So u for us is equal to big velocity vector. Is a one-dimensional flow, basically. So how this integration is done? The integration is done in the following way. We have this area A1, which is equal to A2 here. And then we have A3, for example, here, which is equal to A4. So it's basically a rectangular control volume. And this integral, equation 8.7, it transforms to just a sum of integrals. First integral, it will be 4 integrals, right? Integral on area A1, integral on area A2, integral on area A3, and integral on the area A4. One comment here is that we have flow always parallel to A3 and A4. So in this case, velocity does not enter and does not exit from the control volume. So this integral actually will be equal to 0, A3. Integral of A3 will be equal to integral of A4, area integral, and will be equal to 0. Because velocity is equal to 0, so we do not have any quantity to integrate velocity in the direction of the edge, because all flow is parallel to our flow. Okay, so we basically have integral of area 1 and integral of area 2. And in the book you can see that A1 and A2, they are same A, so I can just improve here and write just A, same value. Left and right area is just A. And it's here in the formula. Okay, so it's let's go to see both equations at the same time. We have density. We see the density here, so density. Then product of internal energy plus velocity square divided by 2. And it has sign minus here. Minus is a sign convention. We say that all quantities which enter the control volume are negative, because here we have velocity entering inside control volume, so it's a negative value, so it's minus because of this. And then multiplied by v. Here v is just a velocity, u1, because we have just one component of the velocity, and ds, because it's integral, it becomes a. And then on the right side, when the flow exits from the control volume, we have the same parameters. We have the density, we have the internal energy and velocity in square, we have the velocity at the exit, and instead of ds, we have the area. So basically, this integral here consists of 2 parts. This one. One part is the energy which enters inside the volume, and the second part, energy which exits the volume. Okay. In the same way, we are doing integration of the right side of the equation, right part of the equation. So this integral is this integral. So these are equivalent relations. And now we just reorganize these relations. We may find that everywhere A is in our equation, so we just cancel A from everywhere, from the left side and from the right side of the equation. We just cancel, and it becomes without area inside, and we rewrite such a way this equation. After we modify, this is just a mathematical transformation from one to another, and it's written. This form is important because we see that we meet the definition of the enthalpy. In our case, enthalpy is internal energy plus pressure specific volume product, or internal energy plus pressure divided by density, which is absolutely the same. So instead of writing this E plus P divided by rho, we just write enthalpy, enthalpy 1 and enthalpy 2. Okay, it's finished here, but at the end you will see that it will be also equal to enthalpy 0. It's a definition of the stagnation enthalpy H0, which is a constant for isentropic flow. And I hope I answered how the algebraic form equation 10 was received from the integral form equation 7. I hope it's this question. Practical application of stagnation temperature, stagnation enthalpy. This question is inside the question of forms of energy equation, which we also discussed today. So as we just wrote in the previous question, we have the enthalpy H plus velocity in square divided by 2 called as stagnation enthalpy. This actually is a valid relation in our calculations, and it's very useful. It relates two different points in space. One point of the flow which is moving, and second point in the flow which is stopped, stagnation point, v equal to 0, and some velocity in the flow. This gives us the following. Okay, I will extend here. One of possible applications. If we assume that our flow is isentropic, when this equation is valid, we can easily assume not just these 2 points, but we can assume any point in our computational volume. Okay, for example, flow outside of this stagnation point going in some other arbitrary direction. If this flow is isentropic, then point 1 and point 2 already observed are also having same stagnation properties for any point in space, and also for our curve where we are interested to calculate the flow properties. So how it can be done? For example, V1 is our initial condition. Initial condition means that we know all flow in this section. Section 1 is the inlet, for example, for our flow. So we know what was the velocity here, and definitely we will know what is the temperature there. So using this formula for the stagnation enthalpy, I will write that Cp multiplied by temperature 1 plus velocity 1 in square divided by 2 would be equal to stagnation enthalpy. From this equation, I already know all parameters. I know what is the temperature, I know the specific heat, I know the velocity. So I can definitely calculate the stagnation enthalpy. And I assume that my flow is isentropic. So this stagnation enthalpy constant for any point in my space Also for this line where I'm interested to calculate the flow properties. In a very simple way, we can measure one of the parameters that we can, and the other parameter we can calculate. For example, very simple, to put some thermocouple here in this point and measure temperature. This will be temperature 2 in space. Thermocouple can be really, really thin, really reliable sensor. It's very simple sensor. It never has moving parts. So it's basically no problem to measure temperature in this flow. And flow practically will not be disturbed. So you will not reduce the flow quality. Measuring temperature 2 and applying to the equation, we can easily calculate what is the velocity at this point. Just the following way. We already know our stagnation enthalpy calculated previously, right? And we will write that its stagnation enthalpy will be equal to Cp multiplied by temperature T2 plus velocity 2 in square divided by 2. And from this equation, the only unknown parameter is our velocity. So we calculate the velocity at point 2. This is one of possible applications of the stagnation enthalpy concept and stagnation temperature concept. This is an answer to the question why can be important, what is the physical meaning of the stagnation enthalpy. If we assume that it happens in our flow, that we have no heat transfer, then we always can rely on this parameter as a constant parameter in our system. And just measuring one parameter, we can get other parameters in the flow. Because velocity, for example, here, this velocity, which I showed you how to calculate, is very difficult to measure by instruments. Temperature is very simple to measure by instrument. You just put thermocouple there. If it's small, it will not disturb the flow. So it's simple to measure. But the velocity is hard to measure because velocity has the value, right? If you put some sensor to measure velocity, for example, some sensor, flow will go around this velocity and will disturb this velocity. So what you will measure is the question, because we'll create a kind of boundary layer, a turbulence around this sensor of the velocity. And then you need to make a lot of corrections to understand actually what you are measuring. So to measure velocity is not easy. And to measure the direction of the velocity is not easy. But it's easy to measure temperature because sensor is much smaller and technically much simpler to do it. And with equation of stagnation enthalpy, we can, just measuring temperature, we can calculate the velocity value. This is one possible answer to your question about stagnation enthalpy and stagnation temperature, but there are more other applications we might see. If you read carefully, please go to read carefully the chapter of forms of energy equations, and you will see that is not only the velocity you can calculate practically any thermodynamic parameter. If you know some stagnation parameter and you measure another parameter, any of the parameters in the flow, for example, temperature, you can calculate not just the velocity, but you can calculate pressure, you can calculate density in this arbitrary point. So it's a very powerful tool, actually one of the most powerful tools we have in gas dynamics. I would like to go to a question about V2, which was equal to 0. It's chapter 8, forms of energy equation, and there are many examples how energy equation can be transformed. So in one moment we have the following form of the energy equation. Let me write here, relation between two arbitrary points in space, of course, point 1 and point 2. And the formula is the following, that A1 in square, A is the speed of sound, at point 1 divided by gamma minus 1. This is analytical formula obtained from also energy equation, as you can see from the book, plus velocity in square, u1 in square divided by 2, would be equal to a constant value and would be equal to any other point we may find, a2 in square gamma minus 1 plus velocity 2 in square divided by 2. This equation can be written for any two arbitrary points in space when the flow is isentropic. Actually, I think isentropic flow is the best application for this kind of problem. In this case, in the Anderson, point 1 and point 2 can be any points in space. It's not limiting us to have some specific value of speed of sound or some specific value of the velocity. It can be any point in space, including it can be a stagnation point. So one possibility, a stagnation point. Point 2 is the stagnation point. So velocity 2, u2 equal to 0. What happens in this point? Since velocity 2 equal to 0, this right side of the equation will not exist anymore. Okay, I will just remove it from here. Okay, it's just 0. And we have just this part of the equation here. Since it's a stagnation point, we usually have T0, P0, rho 0, right? Rho 0. And also A0 becomes here, A0. A0 is called the stagnation speed of sound. Can be calculated as any other speed of sound by formula, but we need to use a stagnation temperature, gamma RT0. Oh. Like this, in a very simple way. It does not mean in the discussion of the book that U2 is always stagnation point. No, it's just a particular case. That let's assume that point 2 is stagnation point, then this equation becomes this equation here. And what is the most interesting, most important from this equation is this right part of the equation. We say that stagnation speed of sound is a constant value. And I think it's quite obvious because stagnation temperature is also constant. Okay, since T is constant, gas constant is constant, adiabatic is also constant. So stagnation speed of sound in square divided by gamma minus 1 becomes also constant value. What does it give to us? Also another possibility that once we know stagnation speed of sound in our computational volume, we know it for any arbitrary point in space, so we can use for any point we want in this computational volume. Same thing, same approach, you may find a bit further, and for my opinion, it's a bit more complicated question, which was not asked yet, but I think it's very interesting, and I would like to explain to you right now that this equation can be written in other form. For example, this point, let's say, okay, somewhere in the middle here, we have a point number 3, and this is a specific point where velocity of the flow is equal to the speed of sound. It can happen, of course. Velocity of the flow can be equal to speed of sound, can be smaller than speed of sound, can be higher than speed of sound. In this particular case, we have velocity equal to the speed of sound. So I will write that my Mach number, which is the velocity divided by speed of sound, is equal to 1. Okay, is equal to 1. So let's write this equation, rewrite this equation in case of this point 3. I will write that A3 in square gamma divided gamma minus 1, sorry, plus instead of flow velocity, I will write A as well because they are equal. Will be A in square 3 divided by 2 and will be also constant as before, and I will remain this part here is equal to A0 in square divided by gamma minus 1. What can we see from here? Okay, this left side of the equation, it can be put on under same denominator, and I will just rewrite this left side. I will put A outside of the brackets. It will be A3 in square, and inside brackets we will have in the numerator gamma plus 1. In the denominator we will have 2 multiplied by gamma minus 1. Okay, this is the equation. What we can see from this equation, we know that it's constant left side, constant right side. Since all gamma are constant values, right, and A0 is a constant value, we also can find that A3 will be constant value. Since all parameters in this equation, the left and right side, are constant, then A3 is also constant. So as a consequence from this formula, we find the following. If we have a flow where we have Mach 1 in the flow, this is called characteristic point. Point where flow velocity equal to the speed of sound. At this point, we have a speed of sound called characteristic velocity. This point will be constant for all the computational volume. Okay, if at some other point, let's assume I will take another color, some other flow direction. We have some arbitrary point, other arbitrary point where we meet Mach 1. At this point, it means that speed of sound will be equal to already calculated speed of sound before. So speed of sound will not change. If you find Mach 1 in the same point in space, in a different point in space in the same computational volume, you will have absolutely same speed of sound. And since we have absolutely same speed of sound, A3 is actually in the book you may find not A3, but you may find is A asterisk, is other denomination, characteristic. Speed of sound, characteristic point. It will be defined for all the volume of the flow, and from here we can find that is equal to gamma RT characteristic by the same formula as we had for calculation of stagnation point, same point, characteristic point, relation between speed of sound and temperature is absolutely same, but we use another temperature. And this temperature, as you may find, since A is constant, characteristic temperature is also constant. So once calculated point of Mach 1 in our computational volume, if in any other point we have Mach 1, we already know what will be the speed of sound, and we already know what will be the temperature of the flow. Going back to our discussion, if we know the value of the temperature of the flow, going back to this picture, we know everything using the definition of stagnation enthalpy. We know the temperature, we can know the velocity value. So, knowing the velocity, we also know pressure and density. This is super important to understand that once we define this characteristic point, we basically know all flow properties inside this point, no matter where it will happen in our space, where it will be physically in our space. We just need to define where is the characteristic point, and we know all the flow properties there. So it's so nice. You already know what are the flow properties, but you just need to know where is this point physically. Okay, this is an explanation about question about velocity 1, velocity 2 characteristic point and setter. So this is not just T asterisk, it also will be P asterisk, characteristic pressure, characteristic density at this point can be calculated all together by its corresponding formulas, but it can be calculated quite easily, all one by one. So we just need to know where is this point, and we can know all the flow properties at this point, no matter what are the other points, right? What is the shape of the body and set. Okay, I hope I answered your question. This is equation actually 835 in the book, page 566. After this discussion, you go directly to isentropic relations, and isentropic formulas that relate relation of pressure as a function of Mach number, temperature as a function of Mach number, and density as a function of Mach number. 3 different functions. But these are analytical functions which we may use for our calculation. They are analytically obtained here. So these functions are exact solutions of the flow equations, and they are extremely precise. In the book, we have equation 44, 45, 46. T asterisk divided by T0. Since T asterisk and T0 are constant values, as we already saw from previous discussion, is 2 divided by gamma plus 1. And P asterisk divided by P0 is another function. Okay, I will write this one. 2 divided by gamma plus 1 powered by gamma divided by gamma minus 1. And these are constant functions. Probably you understood, because this right part here and this right part here are constants. So it's not changing, not depending on any parameter of the flow. What does it give to us from the practical point of view? To understand, we must go to see a simple example. I will draw to you a simple tank like this. And in this tank, we have high pressure. This P0, which is much higher than ambient pressure. And this makes us to have a compressible flow. If we have pressure close to ambient pressure, PA, which is outside, then flow can be compressible, can be incompressible. So we don't know. We don't know if we have T0 and T asterisk and P asterisk. What is the asterisk parameters? They are parameters, as I already told you, where Mach number is equal to 1. So we must have a flow velocity equal to speed of sound. For this, we must have quite big pressure difference to have enough potential energy to accelerate our flow. So flow is accelerating practically from velocity equal to 0 here. So if the velocity inside the tank is equal to 0, we have stagnation pressure. And here, this is the nozzle of our tank, and in this point we have Mach 1. Mach 1. What exactly should be the pressure? We will discuss a bit further, right? No, we already can do it right now, but okay. It has also relation with the ambient pressure, and it will be not now. It will be after we study some more theory. If we have Mach 1 at the exit of the tank, we have same time P asterisk and we have T asterisk. Same time here. So these two formulas allow us to calculate this P asterisk and T asterisk on the exit of the tank. It will be flow, right? And the temperature relation, having the temperature relation, we can calculate the temperature in a very simple way. Just T asterisk would be equal to, okay, let's multiply 2 T0 divided by gamma plus 1. Let's see how much it can be. Is 2 here in numerator, and in denominator gamma I will remove. Gamma plus 1 will be approximately 2.4. Okay, so 2 divided by 2.4, you have a decrease of temperature. So you will have this temperature calculated based on temperature inside the tank. In the same way, you can calculate the pressure ratio. So P asterisk would be equal to 2, here 2.4, okay, and here gamma divided by gamma minus 1 is 1.4 divided by 0.4, like this, and this is approximately 0.5. Approximately 0.5. Exact value, I think, yeah, we have in the book, it's 0.5 to 8. 0.5 to 8. And for the temperature is 0.833. Okay, so if we know pressure and temperature inside the tank, we can know what will happen with the flow. If we have a sonic flow in the exit of this tank, what will be the pressure and temperature parameters at the same point where Mach number is equal to 1. So this is a practical application why we need these two formulas, T asterisk divided by T0 and others. Okay, I hope it's clear. It's a very practical formulas. It's not something that we just receive theoretically, but it's a super practical formulas. We already know, okay, we have, for example, 10 bar inside the tank. We have 10. So using this formula, we will obtain that in the exit of this tank, we will have 5.28 bar. Okay, and we have, for example, 300 Kelvin inside the tank. In the exit of the tank, we will have 300 multiplied by 0.3833. Very, very simple relation given to us the answer, what will be the flow parameters at the exit of the tank where Mach number is equal to 1. Please also remember that for all temperature parameters, we use Kelvin in these formulas. We do not use degrees of Celsius. Okay, no degrees of Celsius, and pressure can be used in a pressure ratio formulas, any units of pressure. But when you calculate, for example, using the equation of state, P equal to rho RT, you need to use all the C units to have a correct calculation. For example, pressure in Pascal here, right? Kilogram per meter cubic. The gas constant in joule by degrees by kilogram, and temperature in Kelvin. All C units. Okay, thank you for participation today and have a nice time. See you then.